Imagine you are driving a boat upstream against the current of a river. Suddenly, a gust of wind blows your favorite height into the water. You don't notice it right away. In fact, you keep cruising upstream at a constant throttle for exactly 10 minutes. Finally, you realize it's missing. You turn the boat around right away and cruise downstream with the exact same throttle to rescue your head. Here's a textbook physics problem that has stumbled thousands of students. If you eventually catch up to your head exactly 1 kilometer downstream from where it fell, what is the speed of the river? Most people's first instinct is to use the riverbank as the reference frame, which is a totally natural first thought. We can try setting up the equations for the ground speeds of the height, of the water, and the boat, and find the mathematical relationship between them. But doing it that way gets really messy. You have to account for the fact that the boat's ground speed going upstream is completely different from its ground speed going downstream. But what if I told you that you don't need any of those speeds? You don't even need a calculator. You just need to completely change how you view this event. Let's rewind and watch this exact same event again. But this time, we are not standing on the riverbank. We are going to look at it from the perspective of the water itself. Imagine our perspective is locked entirely on the flowing water. We are drifting right along the current. From this point of view, the head is not moving at all. It's just bobbing peacefully in place. But what about the boat? The boat has a constant velocity relative to the water, and let's call it VBW, which is the velocity of the boat relative to the water. Because the throttle doesn't change, the VBW remains absolutely constant. So in the water's reference frame, the boat simply drives away at VBW, and when it turns around, it comes right back at that exact same speed. Think about what that means. If you drive away from a stationary head for 10 minutes at a constant speed and turn around, it's going to take you exactly 10 minutes to drive back. 10 minutes out, 10 minutes back. And this means the height was sitting in the water for exactly 20 minutes in total, right? So what happens to the height during those 20 minutes? The problem tells us it drifted exactly 1 kilometer down the river. If an object moves 1 kilometer in 20 minutes, which is 1/3 of an hour, its speed must be 3 kilometers per hour. And since the head is just floating along with the current, the speed of the head is exactly the speed of the river. So there it is, the river is flowing at exactly 3 meters per hour. We just solved the problem in our heads, but if this shift in perspective still feels a bit abstract, let's use a more familiar visual analogy to lock it in. I want you to imagine that this flowing river is actually a massive, slowly moving train. Look at it from inside of the train car. The surface of the water is just the solid floor of this train. The height is an object dropped on the floor, which is just sitting there perfectly still. And the boat? That's just a passenger walking down the aisle at a constant walking speed. If you walk down the aisle of a train for 10 minutes and turn around, obviously it takes another 10 minutes to walk back, then 20 minutes in total, right? While that passenger was doing his 20 minutes round trip inside the train, how far did the train itself travel? It moved 1 kilometer down the track in those 20 minutes. So 1 kilometer divided by 1/3 of an hour gives us exactly 3 kilometers per hour. It's the exact same logic, but just mapped to something that our human beings intuitively understand. This is the magic of the relative velocity. If a physics problem feels impossibly complicated, you are probably standing in the wrong reference frame. The moment you step inside the right frame, the math completely disappears, and the universe just makes sense. If this 3D visualization helped you finally see the physics, hit that subscribe button. Let me know what impossible physics problem we should visualize next in the comments below.